Welcome to a brand new episode of Machine Learning Made Simple. Here we unravel the enchantment behind machine learning, demystifying all the technical jargon. I'm your host, Shogato, and I'm here to chat with you about the revolutionary changes unfolding right before our eyes in the tech world. Let's dive in. Welcome to another episode of Machine Learning Made Simple. In today's episode, we will focus on the multimodal vision models. And the reason is because these models have been coming out like candy in the past few months. AI wave goes through phases and looks like the latest wave is the wave of multimodal vision models. And many vision models came out. The most prominent being the Llama 3.2, which I covered in a YouTube video. If you're interested, I'll post a link. It's very interesting. You can just pull very easily using Ollama and just run it very quickly. So that's not the only game in town. Llama 3.2 vision is already old news. There are many vision models that come out. In fact, Llama 3.2 vision has an upgraded model, which is the Vision Guard, which provides the guardrails in case people try to use nasty images for inferencing purposes, just to play prank on the model. So Llama Guard, Vision Guard is the next level. In fact, enterprise architectures should look into that if they're willing to incorporate Llama vision models into their architecture pipelines. So for on-prem models, or doesn't need to be on-prem, it can be deployed on cloud as well. It means it stays within the enterprise. It doesn't go out to a third party like OpenAI or Anthropic for inferencing purposes. So the whole point of using the Llama models is to keep your PII contained, your personal information, your secrets, your enterprise secrets contained within your organization, and very easily using technically on-prem, because you still probably have to deploy it on cloud because of the resource constraints for on-prem. If you have GPU for your architecture demands, then it's great. But if you don't have GPU for whether you're a startup or a large organization, doesn't matter, wherever you deploy this, on-prem, on cloud, these models help you contain your PI, your secrets, organizational secrets, and enterprise architecture within the organization. So these vision models are great. These models are great, and that's why I'm so much in favor of these models. So that being said, so let's talk about what are the new developments in this arena. So a lot of models have come out after Llama 3.2 vision came out, like in quick successions. Now people are releasing fine-tuned, smaller model, like talk about a model which is only 700 megabytes, like tiny model which are performing exceedingly well. It reminds us of the older models, vision models, which are very good for visual question answering. Remember, we covered this before. Vision understanding is nothing new. Researchers have been working on these models for a while now. In fact, it goes all the way back to those models which were used for visual question answering. In fact, Clip Encoder is one of the top models that came out and like surpassed all of those, and Clip has so far been used, and Vision Transformer. We talked about all of those things. Clip, Vision Transformer, Lava models, MGIE, all those models have been out there for visual question answering, and they are just getting better. So we will get into the nitty-gritties of this, but let's do a quick overview of what these models are. We'll start with the Llama models because they are the most popular models, and then we'll move on to the other models that are in the market. So what is the Llama 3.2 model and how is it built? Essentially, Llama 3.2 model is a distilled version of the Llama 3.1 model. You've probably heard of Llama 3.1, 405 billion model. It's enormous. It takes like a massive GPU cluster to host. I mean, on-prem is probably not even an option unless you have a GPU cluster at your disposal. So what they do is they take the Llama 3.1 4.405 billion model and distill it down. It's called knowledge distillation, and we'll talk about this more. But before that, let's quickly look at what Llama 3.2 is and what are its capabilities are. Now, there are a couple of ways we can deploy Llama 3.2, and if you have watched my YouTube video on Llama 3.2 deployment using Ollama, then you probably know by now that you can use Llama 3.2 with Ollama. You just a Ollama pull of the Llama 3.2 vision model, and you can just start using it. And if you're interested, I'll post a link and you can follow the video and try it out yourself. It's very simple to use. Llama 3.1 is already a multimodal, which means it can ingest images, it can even ingest videos, and people don't talk about it much, but we'll show in the paper that they have published how the video images, video content is encoded into the processing pipeline, and we'll talk about that later. But just to clear the air, Llama 3.1 is capable of everything Llama 3.2 Vision can, but it just kind of is a big model. So Llama 3.2 Vision, so it is multimodal and multilingual. So it can understand languages. So if you give it a poster in Spanish, it can extract the information and translate it into English. So if you have a poster in Spanish, and then if you want to decipher it, and you have Llama 3.2 Vision running on, let's say, your phone or any edge device using an API, it's kind of hard to run it on a edge device like that. But let's say you can take a picture and send it to a cloud inferencing pipeline which is running Llama 3.2 Vision. Then it can translate Portuguese, Spanish, or different languages into English very quickly. Google can do the same thing, and it's much faster too. But the beauty of Llama 3.2 is that it's free, it's open source. Google Gemini models which you're using to do the translating of those images of different languages into English is probably not free. It's available for free for you to use, but you cannot use it commercially. You cannot build an app around it. For Llama 3.2, you can build an app around it. So what are its capabilities? Let's say we can input an image and say, where is this located? And what are the attractions nearby, right? So then let's say we enter an image of the Grand Palace in Bangkok, Thailand. It will be able to recognize the location. And not only it will be able to recognize the location, then once it recognizes, it can ingest and find out everything about it and tell you the rest, like what are the attractions nearby. You'll be able to know, like what are the attractions near the Grand Palace in Bangkok, right? Or you can insert an image which is a drought map of the entire world, right? So then it will be able to decipher the label and all those things, and then it can extract the information. And we looked at this during our video. If you're interested, go look at the YouTube video we did. It can extract enough information. So the most important thing that startups, founders, or business use cases would be, given an invoice, can it extract information? And the answer is yes. And the reason it can do it, and we'll review the 3.1 architecture later. The 3.1 has inbuilt OCR in it. Okay, and we'll talk about it later when we look at the architecture. So these are the things that it can do. It can look at an image and identify where it's located. If it's a famous building, it can identify, for example, Bill Gates in an image. It can identify and read charts very well, and we looked at that. One of those capabilities, it can extract flowcharts. It can extract information from charts, graphs, flowcharts, and definitely it can do OCR. So it can do all those things. And then, of course, there is benchmark. People have benchmarked it, and it does pretty well in those benchmarks. It's probably not as good as GPT-4, but it does pretty well. Now, if you look at the Hugging Face page, so there is a video part of this podcast, and I'm going through this simultaneously, but audio portion, you probably won't need to see that. But so I'm going to read what it says. The 3.2 license has gone through a change. Meta Llama has been disallowed to access this model in the EU. So if you're in EU, then you probably won't be able to use it because of the regulatory compliance issues. Okay, so for good reason. So has EU shot itself in the foot and crippled themselves in the AI race? Probably. And people have been talking about this. The EU regulations have become so strict, and they have come in a little bit too fast. And they kind of have stifled the development of AI. So they're going to have some setbacks in their development in the AI race. They're probably going to lose out in the AI race over time. So we'll see. I mean, I cannot comment much what will happen in the future, but it looks like the regulations have been a stifling factor in the progress of the AI in the EU space. So let's talk about what's special about the Llama 3.2. So Llama 3.2, as we will look into more detail in the next segment, is essentially a knowledge distilled version of the 3.1 multimodal model. So the 4 and 5 billion models. And there are few ways they do the knowledge distillation, which we'll talk about later. But given that knowledge distillation, it inherits all those capabilities of 3.1, right? Not as good, but most of it, right? Assume that I'm teaching someone most of the things I need to be in a meeting. Let's say I'm sending my representative to represent me in a meeting. I don't have to teach them everything that I know, just what's relevant for the meeting. So these distilled models are like that. They know sufficient amount to be able to perform well in those tasks that they are given, but they are not well versed for the diverse range of tasks that Llama 3.1 multimodal can perform. So these 3.2 models are capable of doing very specific set of tasks very well, but they're probably not capable of doing those diverse set of tasks that the 3.1 model, the large model, can do. So now there are few flavors, and these are called the herd of Llama models. There are a few set of these Llama 3.2 in the Llama herd of models. So you have the Llama 3.2 1 billion model, you have the Llama 3.2 3 billion model, and then you have the 8 billion model. And now they are the instruct versions. So the difference between the regular models and the instruct versions is that the instruct versions are well suited for prompt alignment. They are usually trained using DPO, direct preference optimization. So they are very good for chatbots, right? So if you're going to use these in a chat-like fashion, so it's better to use the instruct models because they're instruct tuned to align to human values and the way human beings talk. So let's have an example. So let's say I ask a model and ask us like, oh, what is the weather today? There are a couple of ways it can answer. It can just give a curt reply. The weather, the temperature outside is 72 degrees Fahrenheit, and that's it. Or it can say, the weather is nice today. It's 72 degrees Fahrenheit. It's going to be sunny the rest of the day. I hope you have a great day. Which one do you think would be preferable to a human being? The second one, of course, the second one. Unless you're a nerd, you prefer a quick and prompt reply, which I would, but most people are not like me. They prefer a polite response. Now, the polite response that the LLM gives is a learned behavior, and that's where the AI alignment comes in. So given those two set of responses, the model is trained to choose the second option, and that is done by those DPO, direct preference optimization. In fact, there would be a human labeler who gets those two options and chooses one of them. Of course, they are going to choose a more polite version, and the model slowly learns to give the polite response. So this method of training the large language model to align them with human style responses is known as direct preference optimization, and we'll talk about this in the future. But we talked about a precursor of this, the RLHF, which is the big umbrella paradigm of this DPO PPO thing. The RLHF is essentially reinforcement learning with human feedback, which is meant, the whole framework is meant to align the human like responses from LLM to align those LLM responses to human values. And the reason for having this framework and to have human feedback instead of letting the agent learn itself what the humans prefer is because the space is almost infinite. It's almost impossible to learn the human preference without knowing a little bit what the human preference is. Like, unless we have like infinite amount of label data set, it becomes increasingly computationally almost impossible to figure out what is the correct reward function to find that human preference. So it's better to have the human beings teach it directly using these two options, like, curt response, polite response. Which one do you prefer? The polite response. The machine doesn't know which one is the polite response, but the human being does. Now, if the machine has to figure it by itself, which one is the polite response, it will probably take them an infinite amount of time, because it's almost impossible to know unless it has finished exploring the entire space. So it's almost impossible. So hence the human feedback. So given the instruct-tune model, we we can choose to either use the instruct-tuned model or the regular model. If you're using for chat completion, chat deployment, then we're going to use the instruct models, the three of them, 1 billion, 3 billion, and 8 billion. Or if we are not going to use for chat completion, if we are just using it for, let's say, extracting vision information, let's say we send it a flowchart, architecture diagram, and say, hey, extract information from this architecture diagram, extract the metadata, extract what they're talking about, and we're going to use it to build our documentation from these flowcharts because the documentation is non-existent. Then we're going to use the regular models, not the instruct-tuned models, because we are not going to use it in a chat completion mode. So, and then they have their own levels of accuracy based on the models that we use. We also have to remember that the Llama 3.1 model also have the tool use capability already embedded into the model, so it can perform tool calling, and we don't want to get into that right now because it's kind of a tricky subject. The tool calling, we did cover it when we covered Toolformer. If you're interested, go back and look at the episode when we discussed ToolGen, Toolformer, all those tooling capabilities of the AI agents or the agentic capability of the large language models. But for now, we'll just not talk about the tool calling ability of these models. So now, given these models, all these 6 models of Llama 3.2 Vision, there are a couple of ways we can use it. We can use the Hugging Face architecture. We can the Hugging Face have already implemented the scaffolding for these models, so which means you can just do a transformer import pipeline, give the model ID, Meta Llama 3.2 3 billion instruct, save that, and the pipeline will, the transformer pipeline will, the Hugging Face transformer pipeline, not to be confused with transformer architecture. The Hugging Face transformer pipeline will automatically call the 3.2 3 billion instruct. If it doesn't have the model on your computer, it's going to pull the model from the Hugging Face space and download it to your computer and run the model, and then you can just start talking to it, chat completion, and the way you want to do it. So, and if you want to use the vision model, then you have to call the vision instruct. Now, they do mention that, of course, they don't have to mention this, but the vision model will be substantially bigger. You probably need 10 gigabytes of GPU RAM to run the vision model. The thumb rule is, and I found this, that they say 10 GB, but usually it takes a little bit more because there are overheads from the weights and other things that are running. And of course, remember that if you plug in your monitor to the GPU, then your model might lose some of accuracy because some part of the GPU memory is already occupied. Your window manager is probably using already 500 megabytes of that memory GPU RAM if you plug in. So one way around it is to, if you have a NVIDIA GPU that you're using for inferencing, keep it separate and only for model inferencing purposes, and buy a cheap GPU, can be NVIDIA or any other GPU, buy a cheap GPU just for your monitors, okay, so that those memory doesn't get shared. You have as much memory as possible, because memory is king right now. With this GPU inferencing, large language models, memory is king. The processing power is not so much, but you really need more memory. More is good. The more memory you have, more GPU memory RAM you have, the more is better. In fact, I kind of made a mistake. I got the latest GPU with less memory. I should have spent the same money to get a slightly older version GPU with more memory. So if you have to choose between, let's say, 4080 NVIDIA 4080 RTX with 16 gigs of RAM and 3090 with 24 gigs of RAM, which are comparable in price, go for the 3090 with 24 gigs of RAM, and even better, get 2 of those. Okay, if you get 2 of those, I mean, that's, you're pretty much set for most of the tasks. You're pretty much set. Okay, so and there are a few other ways you can run this. So coming back to how to run these Llama Vision models, you can run with OLlama like we talked about, and it's pretty simple. You just do OLlama pull or OLlama run x/Llama 3.2 Vision, and this is important. It's not Llama 3.2 Vision, it's x/Llama 3.2 Vision. So that's, you can run with OLlama very quickly. Or you can just do a Llama CPP, but if you're on Mac, just do a Brio install of Llama CPP I say Mac is preferable if you don't have a GPU, because Mac have this integrated memory architecture which allows the GPU, every computer has an integrated GPU now, that GPU can share your CPU memory on Mac. So that's interesting for Mac. So Mac users can run models, and I have done that. It's pretty simple. But if you have a PC, then you do need to get a dedicated CUDA GPU like NVIDIA GPU. You can use ROCm. ROCm is the AMD architecture or the AMD counterpart of NVIDIA, but ROCm is almost impossible to run in Windows because of driver compatibility issues. But if you're on Linux, you probably can make it run it, but it's probably not worth the effort. If you really strap for cash and you really want to build a GPU server with lots of RAM, then you might look into AMD, because AMD is coming out with like a lot of latest cutting edge large memory size GPUs, but they all use ROCm. But making ROCm work with the current architecture of transformers is kind of it'll be a lot of elbow grease, I can say that. Okay, so that being said, we have covered the Llama 3.2 and given an overview of how to use it. You can also use WebLLM, by the way. Some people use WebLLM. I don't use it, but you can use WebLLM. So given all that Llama 3.2 overview, now let's dig a little deeper how the Llama 3.2 is built. We'll go in stages. First, we'll talk about how Llama 3.2 is built from Llama 3.1. Then we'll dive a little deeper into Llama 3.1 itself, the 405 billion model, because we never talked about this. The next segment, let's talk about how the Llama 3.2 is built out from Llama 3.1. Now let's look at how the Llama 3.2 models are extracted or distilled from the Llama 3.1 models. So now Llama 3.1 comes in three flavors, as you probably already know. It comes in the 8 billion pre-trained, 70 billion pre-trained, and 405 billion. 405 billion is a huge model. And all of these are instruct-tuned, which means they have chat completions, AI alignment, prompt alignment, and human values safety guards. Like if someone asks, like, tell me about how to cheat on my girlfriend, they're not going to get a response. And I actually tested that you can't even ask for medical advice. So if I upload an X-ray of myself and ask, tell me the treatment plan, it says I'm not a doctor, I cannot give you medical advice. So it just totally skirts that issue. Although GPT does give that advice because GPT has been trained extensively on medical data, so it has that capability. But Llama 3.1 completely avoids that question. It has safety guardrails built into it. So now these 8 billion model, 70 billion model, and 405 billion model, these are three different models, each trained on separately on separate data sets. Well, maybe not a separate data set, but they're trained separately. Okay, so the 70 billion model and the 8 billion model is not the distilled version of the 405 billion model. They're just independently trained. So how this knowledge distillation works. So how do we take a 70 billion parameter model and distill its knowledge into a 3 billion parameter model? Okay, so let's look at this. So at its core, the knowledge distillation is really a method where a larger pre-trained model, in this case the 70 billion model, called the teacher, transfers its expertise to a smaller model, which is called the student, the 3 billion model. The idea is that the student doesn't need to learn everything from scratch. It can focus on mimicking the teacher's behavior and learning patterns. So in our case, the teacher is the 70 billion parameter model, the Llama 3.1, and the student is the learner, 3 billion Llama 3.2 that we are building, which is ideal for faster inferencing on edge devices like your smartphone or other embedded system. So how does the teacher actually teach? This is where the logits come in. Logits are the raw outputs that a model generates before making its final prediction. So if you have stacks and stacks and stacks of transformer layers, and then at each level the transformer acts on that and produces an output, then it goes a bunch of outputs in a feed-forward network, which are the logits, and then they are passed to a softmax and then converted to a vector and then mapped to corresponding word vectors and to extract which word is predicted next. Okay, so that's how it usually works. So we skip the last two steps. We don't care about the word vector. we don't care about the softmax layer, we don't actually care about the word prediction, we actually need the raw logits, which is the 2 steps before the actual word prediction. So we take those logits, which is almost the penultimate layer, and then we make, instead of before it makes the final prediction, then we're gonna transfer the knowledge using those. Okay, so let's, as an example, let's imagine you ask the 70 billion model a question: what is the capital of France? So now, instead of directly giving the answer, which is Paris, the teacher gives you a ranked list of possibilities and how confident it is in each one. Okay, so these are the logits. So it might say Paris 98% confident, Lyon 1% confident, or Marseille 0.5% confident. So this ranked confidence is much more nuanced than a simple right or wrong, right? But providing these logits, the teacher is essentially teaching the student LLM how to think rather than just what to think. So it's not just rote learning, it's giving a little bit more nuanced approach to this. So the student learns the relationship between the options, even though it might not pick as the final answer. So these are the logits, right? So now we have to pre-train the student as well. For the Llama 3.2, the training begins by incorporating the logits from the 70 billion model in the pre-training stage, and it uses some data. Both the teacher and the student are fed the same data, and the teacher generates the logits. Okay, and the 70 billion model outputs its logits. Essentially, it's a probability distribution over all possible predictions, like we talked about with the Paris. There are like a few possibilities, and it gives a probability distribution over all that. And the student mimics the logits. The 3 billion model now is trained to align its outputs, which looks like the same it gets trained to mimic the probability distribution that the teacher LLM is outputting. Okay, so once it learns all that, then we have to also do a post-pruning, which is called the post-pruning knowledge recovery. The knowledge distillation doesn't stop at the pre-training. After all the training is done, we need to do pruning. Okay, and after pruning, less important parts of the models are systematically removed, and the student will lose some information, lose some knowledge, but that's fine. This is where the post-pruning distillation comes into play. So here the teacher swoops in again, providing the logits to help the pruned student recover any lost performance. So there are 2 stages where the knowledge distillation works. At the first stage, you do the teacher, then the student mimics the probability distribution of the teacher. Pruning is essentially just taking out a few of the layers and setting some of the weights to 0. And after all this pruning is done, then you train it again, and it's like reteaching a trimmed down version of the student. And the reason the pruning is required, because you're essentially distilling a 70 billion model to a 3 billion model, right? Imagine you are trying to fit, let's say, a massive tree into a small bowl, like a bonsai. So if you have to do bonsai of a large tree, you have to prune. Okay, and every time you prune and it grows out a little, you have to prune a little bit more. So the same thing, it's an iterative process. So that's how essentially the knowledge distillation works. And once the knowledge distillation is done, it goes through another process of alignment, AI alignment, the supervised fine-tuning, rejection sampling, direct preference optimization, all the regular stuff that you use for AI alignment, RLHF in fact. So that's how the 3.2 models are in fact trained. So that's how knowledge distillation is working under the hood. So now that we know how the knowledge distillation is used to create the Llama 3.2 model, let's look at under the hood of Llama 3.1 model, and let's see what have they done to make these models so fascinating. So the Llama 3.1 models, they are called the Llama 3 herd of models. There are a bunch. There is Llama 3, 8 billion instruct, 70 billion instruct, 3.18 billion, 3.18 billion instruct, and it goes on till 405 and 405 billion instruct. So there are a bunch of them, and each one have their own abilities and lack of abilities. The 405 billion instruct is fine-tuned, is multilingual, is long context, and can use tools. The non-instruct model cannot use tools. Okay, so that's the primary difference between the instruct and the non-instruct models, is the non-instruct models cannot use tools. You cannot use it in an agentic fashion. So let's dive a little deeper and what they can really do. So there are so many capabilities of these models. So the main ones that we really want to focus on, So they talk about it if you look at the paper, they talk about scaling laws and all those things, and we really don't want to worry about the scaling laws. But I will make a point about the scaling laws is that right now it seems, and there's been news that the large language models are hitting upper limit in AI scaling, that they are not improving even with extreme amount of data and extreme amount of computing resources thrown out at them. They are not improving. The improvement has stalled. So they are not really scaling. The reasoning capabilities are not scaling with the amount of data that they're given right now. Initially, there was a rapid improvement, but no longer. So it is probably stalling. It's plateauing out. Okay, so let's talk about a few things about Llama 3. Llama 3 does something called post-training, and we looked at that when we talk about Llama 3.2 as well. 3 models, also, all of them do post-trainings. So Llama 3.1 does a lot of SFT, which is supervised fine-tuning. So they go through all the process. They do chat dialogue formatting, they do reward modeling, supervised fine-tuning, direct preference optimization, all those things. Like, they throw everything at it. And they also do post-training with preference data and all those things. They go into quite technical detail. Do we need that? We probably don't need all those things, no need to know. So what can it really do? So one of the main features that we probably would be interested in is in a long context. How much? 128,000 tokens. So that's pretty long for an open source model. However, Anthropic has probably that level already. However, interestingly, OpenAI models don't have 180K models, a 180K token limit. Their limit is 8,000. So OpenAI cannot generate or ingest a lot of information, which is good and bad, which keeps the cost down probably, because Claude consistently their tokens expire quickly. So even if you're on a pro plan, you'll see the chat has exceeded its limit, because every time you say something, it ingests the whole thing, the entire chat history, and ingests too much information. And it's kind of a nasty thing with Claude, that your tokens expire, your token limit gets hit pretty fast because of its long context length. But I don't think Llama 3.2 will have that issue, because it's a free model, provided you have enough compute resources to host it. Now, tool use. It has the tool use capability. It can search. It can perform code interpretation for Python. I think they only use it for Python. And they can definitely call the Wolfram API. If you have ever used Mathematica, Wolfram API allows you to perform complex mathematical operations. So all calculus and all those things are already embedded into the Llama capability. So definitely it can call Python and Python interpreter and perform code execution. Interestingly, I haven't seen that being used, but I'll be interested in an AI agent, code generating AI agent using Llama, because that would be one good use cases. So what else can it use? So in the paper, they said, based on the inflation rate of US in February 2024 and cost of this list of tuples containing daily groceries, and gives a list of grocery, and they're like apples is cost $6.25. Can you give me an estimate total cost of my groceries over 30-day month? Okay. So then it calls a tool, which is a URL. Consumer prices rose. So essentially what it does is it can call a URL and find out what is the actual information, inflation rate, and etc. And then what else can it do? This tool calling is mostly URL search. Can it do a calculation? Okay, so it's calling a Python tool. Okay, looks like it has embedded Python tool calling capability. So it can execute the Python code, like simple Python code inside itself, like a inbuilt Python interpreter. That'll be interesting. I'll probably check it out later. Okay, so looks like the tool calling capabilities are limited to internet search calls and Python code executions, which is amazing. And that's enough for me. Can it call an API? Let's say there's a user prompt. What's the relationship between a cereal's sugar content and its overall rating? Can you visualize this relationship and provide a way to estimate a cereal's rating based on its sugar content? And gives the CSV file for that. Okay, so the environment IPython, tool search, Brave, Wolfram Alpha. Okay, so the assistant does a tool call, so essentially generates the Python code and then calls the Python interpreter. Okay, that's good. Okay, this is like what GPT can do. Like if you ask the GPT a similar question that involves calculation, it generates the Python code, executes the Python code, and draws a graph for it. Like if you say, given that this data, like my grocery bill for the last 30 days and the corresponding increase, can you estimate the future cost increases? So it can get the CPI data, the consumer price index data, the inflation rate, and then write a Python code to calculate the next 3 or 4 months or 6 months of price increases and plot it in a graph and display it. So essentially what it does a few things. It ingests your data, calls a Python interpreter, a Python code generator, generates the Python code, calls a Python interpreter to execute the code and generate the graph and displays the graph. So yeah, so that tool calling capability, so there are a few steps there. It has to ingest your data, call a URL to get the inflation data. So that's the tool calling, write the Python code itself, call a Python interpreter, that's another tool calling, and display the graph that the Python code generates, the Python interpreter generates. So now those are the capabilities already we see in GPT-4. GPT-4o and O1 preview has all those capabilities. That's now integrated into Llama 3. So that's amazing. So which means a free model can do everything that GPT-4o can do. Hence O1 came out, O1 preview came out. So okay, so those are all great things. What else can it do? Looks like it can do contamination analysis, but I'm probably more interested in what is the security features. Okay, so they also talk about multilingual bench, and I read somewhat their multilingual capability of Llama is not as good as GPT-4. Yeah, I don't really care about multilingual capabilities. I mean, because I'm not developing an app with multilingual capabilities. I'm more interested in the security features. Okay, so what are the security features? Safety pre-training. Okay, that's interesting. So they talk about the safety, and all of them have their own safety. So each model, Llama 8 billion, 7 billion, 70 billion, 405 billion, have their own safety fine-tuning. So that's an interesting graph they talk about. They talk about the violation rate versus the false refusal rate. So I think as an example, how do I cheat on my girlfriend? That prompt will be refused. They will refuse to answer. But if I say, how do I talk to my girlfriend and another female friend at the same time, probably shouldn't be refused, but let's say that is refused. So that will be a false refusal rate. Okay, so it looks like the model made substantial improvement on safety, and it has looked into slangs. It prevents slangs, and it also blocks unsafe tool chaining, like asking multiple tools at once, one being violating early checkpoints, forcing tool use, modifying tool use parameters. So okay, so they did look at a lot of different possibilities, different possible ways that the models could be attacked, and they have made substantially progress in providing those safeguards. In fact, they have come up with Llama Guard 3, which is an advanced level of guardrails that's provided with this model. In fact, we can probably look at the Llama Guard 3 vision model. The Llama 3 Guard 3 vision model prevents any unsafe use. So for example, if we give it some unsafe image, and it's like it's tax season, or how do we evade taxes, then you'll say, okay, we're not going to answer that. Okay, for your safety assessment, we're not going to answer something like that. Okay, so it does provide those kind of protection. Okay, that's interesting. So we did talk about in depth about those Llama models, and now quickly I'll look at the other models that are coming out, which are not Llama models, but they're also multimodal vision models. Some of them are substantially smaller, and some of them claim they almost have GPT level cognition. So the next up is the Llama O1 model, which says that they have almost OpenAI O1 model cognition capabilities, and this is based on Llama, and Llama is that visual question answering model that we talked about in the introduction. That's where it all started. The Llama model can look at images and describe images, and that's where all the multimodal capabilities started. So here they are saying that this has essentially reached the reasoning capability of GPT-4o1 mini, I guess. So one of the use cases they describe that given a science problem, how does it perform? Okay, so let's say it gives a rectangle and ask an image of a rectangle and ask the complex questions, and they compare the responses with Llama 3.2 11 billion vision instruct model compared to their model, which is Llama o1 model they're calling. Didn't seem very exciting example, but what they're really showing in their paper, if you look at their paper, you'll see that their model is performing in the reasoning capability better than the Llama vision model. Now, that being said, the Llama 3.2 vision model is only for extracting information from images. It's not for visual question reasoning, which is Llama great for. Okay, so it's not for visual question answering. Okay, so they shouldn't have compared this to Llama instruct model, Llama 3.2 vision model. So essentially what they did is that given a question, they can summarize the image, extract captions, and perform reasoning and then give an answer. Essentially, I think they're performing COT, chain of thought reasoning on the extracted information. We can do it in few steps with the Llama vision models too. We can say extract the image and perform visual question answering with that. We just need a few steps. I don't know why they have to create a separate model, but these models the Llama models have embedded capability of visual question answering and reasoning capabilities. It's impossible to tell how the model performs because they have not released the code yet, but we'll keep an eye out and update. The one last model I'll just mention, and the reason I'm mentioning this because it's a vision model, is a multimodal vision model, which is less than 1 billion parameters. I mean, this is interesting, mostly because it's very easy to deploy very quickly. If you look at the model size, is less than 1 gigabytes. Okay, if you there's the F16 version, and if you have the quantized version is only around 500 megabytes. This is very interesting. They do use DPO, direct preference optimization, for model alignment. So I'm assuming this has safeguards in place. I think it works well, but I have to test it out. I'll report as I evaluate this. So we talked about a lot of vision models, the new latest vision models, and we'll create videos on these models as they're coming out, because the audio segment, we cannot really describe what's going on. So keep an eye out on the YouTube podcast segment. So that's it for today. Talk to you. That's a wrap for today's episode of Machine Learning Made Simple. If you have questions or want to explore AI topics further, please don't hesitate to leave a comment. Until next time, keep exploring and enjoy your AI adventure.